Okay, there you go. So it's a pleasure to have Professor Douglas Galvao for the seminar today. Professor Douglas is a full professor at Applied Physics Department at State University of Campinas, São Paulo. He is also a member of the Brazilian Academy of Science and a researcher of the Brazilian National Council CNPq, level 1A. He got his PhD in, I may skip the years, but it's written here, in 89 from State University of Campinas. He was a postdoc at Princeton University and Bell Communication Research in the US. He received many academic prizes, including Young Brazilian Scientist and twice the Zeferino Vaz Prize for Academic Excellence. He is associate editor of the Computational Material Science, Oxford Open Material Science, and a specialty chief editor of the Computational Material Science, Sec Frontier Materials. He is presently the executive director of the strategic planning of the University of Campinas. So today he will talk about simulating nature from nanomaterials to ants. Professor Douglas, a very great pleasure to have you here. So the microphone is yours. Take your time. Thank you once again.
Thank you. Good afternoon. I would like to thank you, thank you and the organizer for this kind invitation. And I will talk about the work of our group in Campinas, simulating nanomaterials and also using artificial intelligence for design new materials. So I will start acknowledging the collaboration with an experimentalists in Brazil and abroad, and also the financial support, mainly from FAPESP and other organizations. And the new developments of software and hardware, computers are not any longer just a tool to help to understand, experiment, and analyze data, but it's a tool in itself to discover new materials and also to analyze new properties that was very difficult before, and nowadays it's a common tool. Among these many techniques we have for designing and study materials, there are two major classes. One is molecular dynamics and using Newton equations, and also the electronic structural methods that based on Schrödinger equation. These techniques has been largely used in nanotechnology and in many applications. I will show some examples what we are using these techniques here in Campinas. So now you have, if you have good infrastructures for simulation, you can choose from a menu that you can start from very small and in just a picosecond simulation up to meters, and also for second simulation. So you can choose from ab initio method like DFT, but it's limited for thousands of atoms. And now you can use a classical molecular dynamics that you can handle billions, literally billions of atoms. There is very common method that's like charms, but now we have a very new development with these reactive force fields for molecular dynamic simulation that it's a revolution in simulation. And you have on the usual scale from mainly engineered application, the finite elements methods. Okay. For molecular dynamic simulation, classical molecular simulation, you just solve the Newton equations that you learn in basic physics, but you need to have a good description of what is called the force fields. That's a potential to describe the interaction among the atoms. Now I will give some examples how to use these techniques for carbon-based materials. I will start with carbon nanotubes, a very famous nanostructure discovered in 1991, or rediscovered, if you like, by the Jima's group in Japan. But carbon nanotube is just a single layer of graphite or graphene, that's a hot topic nowadays, that you make a cylinder. In the same way, if you do with a piece of papers, depend of the angle, the declination angle, you can have different structure. You can have this structure on right, the zigzag structure on left, and a mix of them, the chiral ones. Okay, but for more than 20 years, almost 30 years now, people are trying to synthesize carbon nanotube with specific chirality, exploring atom chain, zigzag, but it has been elusive up to now. It's not possible to produce large quantity of carbon nanotube with specific diameters and specific chiralities. So this has limited the carbon nanotube application in nanoelectronics, mainly in nanoelectronics, and but people continue to search for new methods to solve this problem. Alternative to do this, instead of producing a large quantity of carbon nanotubes, you can synthesize just a few one, but long. But long, I mean centimeter size. This is called carbon nanotube serpentines. This is an example of this experimental work that was pioneered by Ernesto José Levit in Israel, and now other groups know how to do this. Yeah. This is a cartoon how you can make this structure. Use the metal catalyst in the top as usual, and you grow the nanotube very fast and use a gas flux to pull them toward the substrate. At nanoscale, the gravity force is not important. You can dismiss them in the simulation, but here the secret, they step the substrate. The step the substrate defines the serpentine. If you control the flux, you can control the separation of the serpentine. In fact, this is a mechanical problem that is scale independent. If you do this with a rock and a string in some church has these steps, you can produce the same kind of structure. So, but knowing the exact dynamics of this process is inaccessible, even if you have the best equipment. So that's when you can use molecular dynamics simulation to gain insights and help to explain the formation of the serpentine. So we run the simulation using classical force fields, use the silicon oxide, that's the substrate that they use in the experiment. And one of the advantages of the molecular dynamics simulation that you can stop time and follow in detail how the structures are formed. You see here different stages of the serpentine formation. In the end, you see wonderful structures. One advantage of the simulation, you can design your own substrate. For instance, we would like to know if the substrate that's important for the steps, or if it's important for the materials. So we create the substrate from graphite, what's impossible with the present technology, and you analyze the same kind of serpentine formation. Okay? They are similar, but the details are different because a silicon oxide is a thick substrate, while graphite it has very, very little friction between the carbon nanotube and the substrate. Then, using the very simple methods, you can analyze the force profile, the energy profile, and you can explain why this would be different. But one the main advantage of molecular dynamics, you can visualize what is happening. This is a movie with the simulation. You see the carbon nanotube falling, being attracted toward the substrate, and the serpentine being formed. It's quite nice. It's almost what the experimenter have proposed, but the details of the dynamics it's a little tricky. You can do the same thing. Oh, sorry. You can do the same thing for. Oh, this is for substrate. Sorry. Okay, this is for the graphite simulations. You see, because the friction between carbon nanotube and graphite, it's not as thicker as in the steel oxide. The tube slides, it's going almost off the substrate, but it recover and also form the serpentine. This was done in collaboration with José Levitt's group in Israel for the experimental part. So this paper was on the Cobra PRL, and this the second time we got the Cobra PRL with carbon nanotubes. And the secret seems to be the figure. If you play black, red, and yellow, there is a psychology paper that the human brain is attracted to this combination of colors. So making figure with this, and it's good for the brain, human brain. Okay, but carbon nanotube has been also used in many kind of electronic applications, right? But in order to make a transition from the silicon electronics we have today to a fully based carbon electronics, you need to have all the basic elements from the electronics elements. Resistor interconnector has been done, the capacitor has been done, diode has been done, transistor has been done. In fact, the fastest transistor today is a transistor made of carbon nanotube. But one main component was missing. That's the coil. Nobody could make good coil using nanotubes. So this it's very important, because if you do not have the coils, you cannot have a lot of very important application as electromagnetic transformers, motors, so on. So, but one of the experiments that José Levitt used to produce the serpentine, they also could produce for the first time well-formed coil. You can access the both ends, which is a fundamental feature that was missing before, and they produce the first nanotube coil. We run the simulation, we use the same techniques, because one question that we would like to address is it possible that you can form this coil so perfect with like a self-assembly mechanism at nanoscale, and this structure does not spread off the substrate. So it seems the secret for this formation, it's the van der Waals interaction is so strong, even when you consider the thermal fluctuation. The van der Waals force work like a organizing mechanism that allows the formation of the coil. We have an idea, but we will run very long. We are using very long tubes, you can see for the movie, and even under this condition, you see the tube is attracted toward the substrate, and it's the van der Waals interaction is organizing the formation of coil. With this element, we have now all the ingredients to make transition for silicon carbon-based electronic. This paper was in the cover of Nanomaterials. Okay. But going back to this, holding up a graphene sheet. Okay, this is graphene that was now one of the hottest topics in material science. You can imagine any kind of application, from relativistic physics to fermion physics. This was one of the first Nobel Prize award. The first paper was a science paper in 2004, and in 2010 they won the Nobel Prize for the work on graphene. But graphene has not used very unique electronic property. It has also very unique mechanical property. It's the ultimate membrane. It's just one atom thick. You cannot go below that. So it's a record that cannot be broken. And it is, you see here, a simulation of a nanoparticle colliding with a graphene membrane. You see the elastic wave propagation. It's almost a textbook of mathematical physics. People has been exploited this property to create a series of applications. This is from McEwen, from Cornell University. They use the silicon oxide substrate. They create a Ethernet, inserted some gas, and deposited a carbon graphene membrane on top of it. One advantage of the using graphene membrane is the van der Waals is so, as I mentioned before, is so strong in this case that you do not need to make it to yield anything. So it's self-depositing, and the system continues on this condition unless a large force is applied on it. So the idea here was to measure the mechanical properties of graphene using this setup. We borrowed this idea in a project in collaboration with Petrobras to design a sensor that could be used in harsh environment. So we have the same idea here. We have the silicon oxide that's basically glass. We deposited a graphene membrane on top of this, filled with gas, and increase the temperature. We'd like to know how is the detachment, if we have leakage or it's a sudden detachment. You see, the simulation showed that it's a sudden detachment. It's a very good if you can use this as a sensor, because it would be a chip and you can work on a harsh environment, and you can use very simple device like a laser or to probe if you have leakage or not. But the fractal of graphene is also very unusual. This is an experiment from Thomas Group at Rice University. They shot silicon nanoparticles on single-layer graphene and multi-layer graphene, and contrary to what you would expect from fractal on standard materials, you do not see the same fractal. You see only this angle, that's called the petal angles, for the fractal. The question, why graphene breaks only with these special angles? We run a very light simulation, use again molecular dynamic techniques, but now using what is quite interesting. It's a new generation of reactive force field. It's allow creating breaking bonds. So it's like you are solving the Schrödinger equation, but we're doing a chemistry without electron, which bring your simulation from perhaps years to weeks. So this is a real revolution in simulation. We can handle a billion of atoms. In this case, we run a simulation with half million atoms. We try to mimic the experiment. We shoot a nanoparticle on a suspended graphene membrane. You can see here from a different angle. You see at the beginning, you have elastic wave propagation that preserves the hexagonal symmetry, but the elastic wave is propagating, it's losing the symmetry. And now comes the interesting part. So I'm showing the movement of a slow rate to see. So we come with in this case, we use a nickel particle. We also use a silicon nanoparticle. So the nickel particles start to interacting with the graphene membrane, forms it, and it has enough kinetic energy to start breaking the bonds. That comes the quite interesting result. See, the fractal here, it's almost the same exact angle from the experiment. This shows how reliable this carbon can be described with this new kind of potentials. In this case, it's a simulation with half million atoms, but we can easily go for many multi-million atoms in less than a couple of months. Okay, but this new force field cannot be used only for carbon or for materials. It can also be used for other kind of non-carbon based material. This is an example of combined DFT techniques. The department has many experts on it, with this kind of reactive force fields. Most of the materials now, graphene created a revolution in material science, right? But up to now, most of the 2D material came from what's called van der Waals solids. You have a lamellar-like structure that you easily separate, but this imposes some limit. There are thousands, or perhaps tens of thousands of structures, 3D structures, that's non-van der Waals materials, that in principle, if you know how to, you could create tens of thousands of new 2D materials exploiting these 3D structures. This is the first example in the literature that this kind of study was obtained. This was in collaboration with Professor Joy in Rice University. Tiara was a postdoc and now it's a professor in India, and Cristiano Volle was a postdoc at our group in Campinas. Now it's a professor in Curitiba. The mechanism, what we call hematine, that's like a graphene from graphite, so we call it hematine from hematite. It's very, very simple to do this. So you take hematite, it's a very common rocks in Brazil. You put it in solvent, and you use sonic exfoliation. So using this technique, you can slice you can cut the covalent bonds along special crystallographic orientations and produce the single layer materials. This is the hematite ore. You grind it, then add solvent, very common solvent, DMF, for 50 hours, and that's all. And you obtain a single layer and few layer hematine. Okay. Then you combine this reactive force field with standard DFT calculation. And one interesting thing here from the DFT calculation, so that the magnetic property, you have one case ferromagnetism, and then when you change the dimension, it goes to antiferromagnetism. And also, it increased the catalytic activity for 200 times. It's a quite interesting material for many kind of application. There is a site that's called the Print Electronic World, that they have the journal that they selected the paper from the universities or academia, and that could have important application in industry. This paper was considered the most significant material science news of 2018. Okay, and also FAPESP funded this. So the FAPESP has a magazine that select some papers and make scientific stories for a broad audience, so that they made this for this. And also the Globe News make a report about this that could, in principle, of course, increase the generation of solar energy, but we know that there is a long way from the basic material to real world application. But this technique is so simple that you use in collaboration with Professor Joyens and Professor Chandra Tiari for use the same concept. Select other rocks or other ores, and use the same liquid exfoliation, creating a new families of 3D materials. We wrote a review paper that was in Cover Materials Today. Also, some electronic piezoelectric application that was in the Cover Nanoscale, and a new paper that just came out. It was in the cover of Small using this technique. So in principle, you can use this material for green energy because they are very abundant. It's not expensive to produce them, and you can produce them in large scale. So it's very attractive from this point of view. Okay, but the real change in nanotechnology is build 3D material from 2D ones, because you do not want a nano car. You want a car with nanomaterial, right? So let me tell a story that now it's 30 years old, and there's three three generations of graduate students. That is work was mainly done in collaboration with Professor Ray Bergman, that's the director of the Nanotech in UT Dallas. And it's three generations of graduate students. Vitor Colucci is now a professor at UNICAMP. Socrates Dantas is a professor in Juiz de Fora. Leonardo is now a professor in Natal. Okay, so three generations of materials, three generations of students. It's interesting. So the first one is we call it buck papers. It was the beginning of this revolution of using fullerene materials. So the buck papers, it's very simple to make if you have the materials. So if you have the nanotubes, just remember the nanotubes, you can have single wall and you can have multi-wall structure, right? So the buck papers make use the same technique the Chinese making white paper for 2,000 years. You just use could be a filter, could be a cloth paper filter. You deposit you deposit the solution containing carbon nanotubes of single wall and multi wall, and smash them, filter them, and you can follow this. This is this exact way you can do a Chinese paper, right? So when used for the microscopy of this material, what you see is something like this, which looks like overcooked. But for more than 20 years, nobody tried a very simple experiment. Everybody knew since the beginning that the carbon nanotube could have could be just single wall and can be multi-wall, right? But nobody tried this simple experiment. What happened with the mechanical properties of these buck papers if you mix them together? So they did this, and they observed a quite interesting phenomenon. You see, depending on the relative content of single wall and multi-wall, you can have transition from non-auxetic materials to auxetic materials. Okay. If you do not remember what auxetic material is, this is a very simple explanation. Most of the material, when you stretch them, they become thinner along the direction you are stretching. This auxetic material have this counterintuitive property that if you stretch them along an orthogonal direction, they expand orthogonal to it. So one way to measure this is the Poisson ratio. If the Poisson ratio is negative, you have auxetic material. The physics of these materials is relatively simple. It's a mixture of bending, stretching. If you do in the right way, you can produce auxetic material. You can do this with a Lego. You can play at home with this very simple model. In fact, there are many toys that use this concept like this. See, kids become fascinated. You see, if they're 3 years old, they become fascinated because they understand that something strange is happening, but they cannot figure out what there is. So as I mentioned, the definition for that material is very simple. Just measure the Poisson ratio. If the Poisson ratio is negative, then you have auxetic material. There are only few of this material in nature, and cork is probably the only natural material that has zero. It's more difficult to find that auxetic one. Okay. That pure carbon structure could be auxetic was based on this was my first papers using molecular dynamics simulation. This is just carbon. The red one are the triple bonds, and the yellow ones as a single and double bond. Okay. Using this polydiacetylene crystal, we predicted that pure carbon material could be auxetic. Nobody could make these crystals in large quantities. But if you forget the material, but keep looking at the topology, this is what we could use as a test for this prediction of auxetic materials. This is the microscopy, and it looks like overcooked spaghetti. If you did this once in your life, when you have this overcooked spaghetti, what you have is bundled together. What make them stiffer and you have the other part of the pasta that are single structures that are softer, right? So you have a combination of stiffer and soft material. So how you model this? In this case, you cannot use fully atomistic simulation or even coarse grain because it's too large for it. So you have to invent a new way of modeling this. Then you could combine molecular dynamic simulation for small models and incorporate analytical expression for the energy and for estimating the Poisson ratio. So this is a real structure. We have to make some simplification, but we cannot lose the physics. So it's a trade-off of the structure, but keeping the physics in it, right? So this real structure is model like this, simplified model. The meandering of the nanotubes are represented by zigzag structure. And we using this concept, we can create a nanotube network that has these two ingredients, that is stretching and bending, okay? So after 2 years of hard work, Vitor Colucci produced this mechanical version of what is the buck paper. How it works, if it works. So using very simple mechanics, you can derive expression for estimate the in-plane Poisson ratio, and you can also derive expression for the Poisson ratio in the thickness direction. And this model works as the first and the most important test. It's that there is a non-auxetic to auxetic transition, and vice versa. Okay, and also you have the limits of this value for the single wall and multi-wall nanotube to optimize. So from this estimation, we see that 2.6 works like a magic number for optimizing the performance. Now, let's go to the test, because physics is an experimental science. You could have a beautiful model. If it fails to describe the experimental data, it's mathematics, it's not physics anymore. So let's look here. This is the experimental data with the arrow bars. It is the black and blue curves at the prediction of the model. See, it's amazing that a problem with this such complex topology could be translated in a mechanical model, and this model has the right physics for this. The paper was published in Science and was highlighted in the first page of the Folha de São Paulo newspapers. Okay. But with the advance of the synthesis in carbon nanotubes, the second generation do not use the bucky papers anymore. It goes directly for what's called the carbon nanotube forest. Do you see an example? Each of this line here, a bundle of carbon nanotubes. If you extract them from this and twist them, you are making the same way as the Chinese make silk. So the first generation is Chinese paper, the second generation is Chinese silk. Okay. This is the forest. You grow here. All this experimental part were in collaboration with Bragg group. You can stretch this. Then you could twist it. This material is so light; it's 10% denser than air. Okay, you can see here from using the nitrogen to highlight it. Okay, this is really cool. So this is the yarn. Okay, what you see here is like Harry Potter invisibility code. So the yarn in a liquid, and you applying a voltage it, okay? You see, it becomes invisible. Why is that? It's the same like in Mirage effect you have in the desert. Because nanotube has such a high thermal conductivity that when you apply a current along them, it hits it very fast, and change the refractive index in front of you. Of course, it's not real invisible, because if you have an infrared detector, you would see the heat. But in the visible, it's quite cool, like Harry Potter. Okay, if you are an old guy like me, remember the circus when you have this what is called the candy cotton, I think. So you push, right? It's like if you see the cotton, the candy cotton forming, is quite similar to pulling the yarns from the substrate, like here. If you twist, you can make the yarn. And these are really, really cool materials. This is an example of this yarn on application. For instance, if you insert these yarns into liquid paraffin, okay, can create artificial muscle that's 200 stronger than our natural muscle. It can stand its weight 10,000 times. Let's see how it works. So what you see here, if the movie works, okay. You see, this is the yarn. You have the pedal, okay? Using just the laser to hit them. Why is it? It's rotating. That's basic physics, right? Paraffin has a huge thermal expansion, about 70 degrees. So if you have a material that is twisted, and the paraffin wants to expand, the only way to have the same amount of momentum, angular momentum, and torques, the system has to rotate, right? Okay, let's see. How strong are these materials? I have the yarn here with paraffin. This is a nanocatapult, okay? The catapult arm, this is wood, and I apply a current here. See, it's amazing. It's very effective. There's a lot of work made for this. I have just few grams here. This is hundreds or more, and I can jump very long because it's very strong. You combine the strength of the carbon nanotube and exploit the huge thermal expansion of the paraffin to make this. Okay, this is the experiment. Now, how model can be used and how model is important to explain what is happening here. Okay, show here a simulation. This is a multi-million simulation, okay, of the formation of this yarn. I'm rotating the yarn, and I have a camera inside the material. What is really cool, because I'm not affecting the material, but I can observe without disturbing how the material is being formed when you twist them. If you cut the real material, what you see is the same thing like you have in the simulation. You have a dual Archimedean spirals. So the scrolled materials are the same. Another thing that the simulation can help is how the strain is being accumulated and being released. Here looks like a continuum, but this is it's atomistic simulation. I have multi-million atoms here, then like this to form the yarn, and I can see how the stress is being accumulated and released as you apply. You can play many different games with this material. For instead of using just the yarn, you can wrap them around an elastomer. And what happens? Let's see what's happened if you do this. Okay. So now I have this material that was wrapped around the elastomer, simple elastomer, and now I look what happens to the conductivity when I twist it. You see here, nothing's changed. Nothing changed. I can stretch it. Nothing changed. That's a little surprise, because if you remember holiday 3, if I change the cross-section of a conductor, the conductivity should change. What you observe here, it does not change. Doesn't matter what you do, the conductivity does not change. You can bend, you can stretch, you can curse it, you can do anything with it, the conductivity doesn't change. How can I explain this? again, it's a problem that needs modeling. You cannot use force breath because it's huge structure. You cannot go for simulation. You have the same kind of modeling that we did before for the stretch, right? So what we did was, this was a nice work of a lead holder that was a PhD student at the time, and now he moved to the industry. More money, work less, smart guy. So what he created here was a model of T phase, okay? And he calculated how the conductivity would change under this condition. Look here. Again, it's amazing that such complex problem could be described in a simple model. This is the point with the arrow band, the blue and black curves are the model. So he explained this. There are many people from statistical mechanics here, but I know it's not the right word for this, but it's like you have a super percolative state. Because when you stretch or bend the material, the nanotubes never lose contact with each other. And the current always flows where the resistivity is minimal. It did explain. It's quite a simple explanation why did nothing change when you do the stretch. Every year, the Discover magazine selected the best 100 all fields of science, and this was the 78th paper of the year, including all fields. Okay, but you can do a little cooler, I think, with it. You said more than 200 years ago, people knew that if you stretch an elastomer, temperature will change. Okay? And the explanation was simple. Because the polymers are disordered, if you stretch them, what happens? You align more the chain, then the entropy decreases. If the entropy decreases, so the temperature should change. And the change of temperature is inversely proportional to the change in the entropy. Okay, this is known for 200 years. But again, nobody tried a very simple thing. What happens if you twist the structure? So if you do something like the yarn, okay? If you do this, modify the elasticocaloric many times. If you insert coordinates, it increases even more. This is from polyethylene, a very common polymer. You can do the same with metallic alloy. But this is, again, an example of all the ideas could be recycled to produce new kind of application. This effect that we call it, it was published in Science in 2019, that's what we call it partial refrigeration by twisted coil and supercoil fiber. The simulation was used to estimate the change. Then you combine analytical models with molecular dynamic simulation to estimate the change in entropy for the polyethylene phase. Polyethylene crystal has two phases, and this phase have different entropy values. Okay, this was a call in the cover, and there was a news on the PBS that the refrigerator of the future may be inspired by the weird physical problem. Of course, this material is not competitive for the technology we have the refrigerator now, but can change 20 degrees by mechanical work. If you are interested in the field, make a barbecue, you can cool your beer, use this. But if you find better materials in the future, we can produce. This is a clean solution for refrigeration. So in principle, it's a very important results, not in terms of the technology in itself, but also, it's a green solution for the refrigeration. Okay, I'm losing. Okay, my time is, I'm running out, so I skip this. And let's talk for the second part of. Okay. If I have time, please ask me about this. Oops. Don't freeze. Okay. Let's talk about ants now. Okay. Okay, we can be very smart and optimize the structure, but there are so free parameters when you render with the real materials that you need better methods, better techniques to optimize your structure. One thing that you can do is use this bioinspired computational algorithms. You see, ants are very, they behave smart as a colony, but individually they are very stupid. Yeah? But they, you see, they are good engineering. They can build, they can behave like a solid sometimes. See, they sometimes they flow like a liquid. They can build tall towers that do not fall on themselves without crushing the ants in the bottom. And the structure are really organized. They can make many other interesting questions. How the stupid individuals can produce such impressive results as a colony? Okay. What is behind this mechanism? Okay. Let's first stress some facts. Ants are blind in the sense that they cannot see more than few centimeters ahead of them. Okay. The secret for the movements are chemical markers, the pheromones. Okay. They create chemical trails. That's the base for their chemical communication. Have two very unique mechanisms. One is the positive feedback, and the other which results in out catalytic process. Most of the phenomena in nature have negative feedback, right? If you do one thing for the first time, you do not have the same feeling if you do the second time, and so on. So the gain in the economy has a negative feedback, and there are many things that have negative feedback. Positive feedback are not common. And even here is the autocatalytic process. For this, one very simple example is learning. The human brain is one of the few processes that they are known for combining also these two things. For instance, if you a physics book like Holiday, so you read first time, you do not understand nothing. Then you read it again. Then you understood a little. Repeat it time, understand better. So what you're doing is a very fine thing. I use the same tool that your brain, doing the same thing, reading the same text, and having different outputs, right? More interesting. There is this eureka moment when, after reading the chapter many times, suddenly you understand what it is. This is the autocatalytic process. A positive feedback leading to autocatalytic process. The human brain is one of the few things in nature that can do it. Ants can do also the same thing, but not with the same performance of a human brain, of course. So people from computer science developed this code that's called ants, because it's bio-inspired by real ants. Okay, Marco Dorigo was on the pioneers, but there are many different models. We have our own models. But there are different models, but based on the same idea. We are trying to mimic on the computer what make ants good problem solver. Okay, and the secret is like this. Okay, suppose that your ants start from the next looking for food, and you have a rock or something that's blocked the way. Then some of them will choose left, some of them choose right. Suppose that the rate position of the chemical market, the evaporation are the same for simplicity. So when these ants in the blue line reach the food, if from the red one has not yet reached it. So and the process continuing, and the ant has this propensity. They prefer to walk on trails where the chemical gradient is high. So after a few of these rounds, the next ant has to decide on the left and red or blue. You prefer the blue because the chemical gradient is higher on the blue. Then after a few things, only the blue F remains. That's just the secret of how ants find food very efficiently. Okay. But you can use the same problem, create a computer algorithm to try to solve problem for us using the same kind of approach. As a proof of concept, I'll give you an example. Okay, polymer has hundreds to thousands of rings, but suppose you have just 3. They are free to rotate along these bonds. If I rotate the first ring in relation to the second by 1 degree each time, we have 360 by 206. So it's 206 multiplied by 206, 3 rings. Multiply this for 1,000, you have more possible solution than the number of atoms in the universe. How can I find the minimum energy using my ants? I explain the proof of concept. So each point on this grid, a possible solution. Which are the solution? The value of the angles among the rings, right? If I have 3, I have only two angles. So each point of angle alpha and each point of angle beta are one possible solution of this problem. Okay, this gives you the angle, the rotated ring around the second ring. Okay, so my ants this space can only work along the x and y axis. Okay, how I use this to find the conformation. I randomly distribute my ants in this space of possible solution. After some runs, I update proportional to quality solution, and I can mix random indeterminate movement. And I can use a taboo condition to save computer time that each point cannot have visited. Okay, but just to say can do not leave. So okay, these are results.
Sorry to interrupt you, but you asked to tell when you have 10 minutes left.
Okay, thank you. Okay, so I solved this by hand because it's a simple problem. I solved by hand in steps of 1 degree, okay? And I plot the map. Even this problem is not as simple as looks because you have 4, by symmetry, you have 4 equal values. If you use gradient techniques, they can fail because it starts jumping from and never converges because if you keep jumping from one solution. Okay. In the background, I solved by hand, not harsh, not very refined grid. Now I let my ants work on this space. See, they are forming the pathway are. Every time it has a good solution, they deposit a pheromone. So that good solution will be receiving more chemical markers, like in the real ants. After a few times, the next ant find the pathway, it follows the same pathway we have a gradient of the chemical mark. Okay, so see, the ants found the four minimum easily. Okay, but this is a simple problem. Just as a proof of concept, I show you that they can do that. Let's go for a real problem that it's very difficult to solve by hand. So I use now another polymer. This is a polyanomaly that has these three different blocks. If I combine these three blocks in different way, I can have from an insulator to have a quite conductive material. Okay? The question is, if I want this polymer to have a specific color and exhibit a specific conductivity value, which would be the best combination of A, B, and C? The number of possible solutions for this problem, it's almost infinite. You cannot do by hand. Our real chemistry do not work in this way, right? He tried to find a good solution, improve on it. Okay. I know that this problem has to satisfy two conditions. If I want a conductive polymer, so the Fermi level should be inside a conduction band, and the wave function at this Fermi level should be the most localized possible. The quality of the solution would be small gaps and high electronic delocalization. These are the two parameters that I create a function and ask my ants to optimize this function. Okay, the optimization of this function will give me the composition of the polymer. Okay, now I let it run. They work very fast. I show again in different view the chemical waste being formed, and okay, they found this is my result, the statistic for the best and best solution. Some of them has been discovered by the chemist. Great, I just discovered what has been done by real chemistry, but also I found new solutions that have not yet been explored by chemistry, which is even greater because so these are possible materials. As I said before, no chemist can explore all the possible configuration of this polymer. So this is an example of this is very effective tools to design materials with specific properties. Could be color, could be conductivity, and in principle can use to optimize any property. But I like ants, so we could also learn something for real ants. I like this paper. This is a paper for a Cuban group published in American Naturalist. Okay, what they did. Okay. This is they collect ants and put them blocked in this array. Okay, and on center of it has a row where they apply insecticide, and then they open the gates on right and left and see what happens. Okay. If they do not apply the insecticide after they open the gates, the number of ants left from left and right are almost the same. When they apply the insecticide, there is a break on left and right. Okay, they speculated that this is because what they call the ants panic is, I would say, hard to believe that, but that the explanation they propose. Okay, what we did the same thing with our artificial ants. So I put a lot of my ants inside a cage, and then I open my left and right gates. What I have see, it's the number of ants living from right and left are almost the same. Okay, this is the real experiment. Now I create a repulsive potential center of it. Okay, make the insecticide. Now I count the number of ants living from left and right, and I see there is a break in symmetry. Okay, gate 1 and gate 2 become different. Here has no panic. So could be that the ants panic, But what we show here that you do not require to invoke and to explain the symmetry break. What we have here is a special symmetry break induced by a positive feedback, just that. Okay, just to finish, I like this. Again, in this, again, using this insect. This is what we call mathematical cigadas. These are we don't have here in the South Hemisphere. They have they exist only in the north, but they exhibit a very interesting behavior. Okay? They incubate only in prime numbers. Some of them incubate in 7, 11, 13, and the longest one 70 years. They remain under the soil for 70 years, exploding in billions of them, and after a few days, the next generation repeat the process. So the question is, why they use the prime numbers? There are many, many theories proposing this. Okay, genetic advance could be evolutionary gain on this. So what we did, we use automatic cellular to simulate with a general model. Okay, we create a prey and we create a for them, and you let the data evolve in time and incubate any number of years randomly what the system produces. And I measure the performance in terms of population. My performance here is if they have more individuals, it seems that doing well. Okay, and I run the simulation many times and count this number. You see, 3, 3, 5. So the prime numbers appears. Is that real? A good test if this is real, if I create a super organism to hunt the prey. If prime number is a good way to survive, this should move to higher prime numbers, because as increase the value of the prime number, the pattern to decode this is become more and more difficult. This is what we use as a key in the cryptography, in public cryptography in the internet. Decomposing, multiplying prime numbers, decomposing them, it becomes increasingly difficult as you increase the value of the prime number. We create the predator, and what we see at what we expect. They move to higher and higher numbers of prime numbers. So you see 17. So the first time that was shown, we use a completely general model that the emergence of prime numbers is a result of evolutionary strategy. Is that real? We never know. But at least in the model, we show that it is possible. Okay. Now I finish this with this movie. I think I like this movie. It's a Brazilian moment again. So we have here our unfunded, not well trained, using old equipment, and we have to compete with people from the first world, well equipped, well trained, and well motivated. So doing science is a competition. You have to solve problems that other people are trying to solve using different tools, right? So the trivial solution for this problem is just to live. You cannot win, right? But sometimes in nature, like the real life, if you're lucky, it works. You keep fighting. That's what we do in this strange time. We keep fighting and hoping for better times. Thank you for your attention. If you allow me to do a little ad, we have a Center for Computational Engineering and Science that's funded by FAPES, where you have many positions available. Diane, that's its professor in your department, postdoc in our group. And these are some of our publications, and these are the topics that the center has. So if you have interest in joining us, please contact me. Thank you very much for your time and attention. If you have questions, I'll be glad to try to answer.
Thank you, Professor Galvao, for your nice talk. Let's see the speaker. So the second seminar is now open for questions. So feel free to open your microphone and ask your question, or just write it down here if you are not, if you cannot speak for some reason. So I myself have some few questions. Let me start them. So the first part of your talk, I had a question about what is the force that attracted the carbon nanotube on top of the substrate, and I think it became clear for me it's the van der Waals force, right?
Right.
Okay. So you at some point you said this is pretty strong, and my question on that is once the carbon nanotube is deposited on top of the carbon, I think it's silicon oxide, right?
So, the experiment, it's silicon oxide.
Yeah. So would it be possible with STM tape, for instance, to reshape the thing on top, since the force is pretty strong? Perhaps it's not possible. Have you investigated this, or is there any experiment on that?
During the growth is not possible because you cannot access the chamber. But after the certain time are formed, you can transfer for another substrate and use AFM if you want to investigate the structure.
So presumably you can design any structure.
Yes, you can manipulate the structure.
Okay.
They played with this.
So in that sense, you can change, for example, the transport property, electric transport property.
In principle you could, but you remember that we are talking about centimeter size structure, right? So your FM in general, the area your FM works is not that large. So probably AFM in this case is not the best approach to do that, because this is a huge structure.
Yeah, it's centimeter, right? It's pretty big. So in your simulation, you at some point you saw some transport, right? So conductivity, and I was kind of surprised that some of this material you can extract and the conductivity is not changing.
Yeah.
Right? They're not changing. So I was trying to think. So which voltage you use to measure this conductivity? Because I was imagining if you have like a 0.5.
It's very simple. You just take two ends and measure it.
So yeah, it's very surprising because if you extract a material, you imagine at low scale, let's say, you imagine the atom become closer to each other. Or maybe this is not true because perhaps they become farther, right? But they change. For instance, essentially they change the distance between them. So you change, for instance, the number of channels, conducting channels. It should appear in the conductivity. Why?
Yeah, but you do not change the pathways because you have so many tubes that they never lose. So in principle, that's a surprise. You deform the material, but inside the material, this is a simplistic explanation, of course, but inside the material, the conductive pathway are never destroyed. That's why they never change.
So, and those structures are responsible for transport, essentially.
What you are doing, you are stretching the material, but the number of contacts is like a super percolative state. I know that's not the right precise definition, but it's like a super percolative state that survives because everything you do not destroy the pathway.
I see.
If you do not destroy the pathway and the current always flows where the resistivity is minimal, then you still have the same pathway.
But it's, it's interesting. If you, I think there is one question here. No, not yet. Andrea said she has to leave. There is a chat here you can access. So I have another question, and this regards the ants. So it's very nice because apparently in your simulation, bug is not a big problem, but that's part of solution. But what are the class of problems that can be solved using this scheme?
In principle, you can solve many problems. That's what we hope that keeps us in the business. But molecular dynamics is a very powerful technique. If you combine with other like DFT, finite elements, in now machine learning, it's entering the field. Then you can design not predict the thermoelectronic mechanical property, but in principle you could design new materials now.
My question perhaps is the other way around. What class of problems the ants this scheme can solve?
Good question. I don't know. We are always looking for a good problem to apply this technique. I think there is a question from Emmanuel Victor, right?
Yes, that's right.
He asked about the invisible cloak. Okay. Yeah, this is from the same group. That's Buggy's group. The explanation is the following. We have the yarns. The yarns are made of billions of carbon nanotubes. And carbon nanotubes are very good thermoconductors, right? So then you create the yarn, you put the yarn inside it, and applied a voltage across the yarn. Okay? Not exatamente the yarn, but the sheet. The yarn, if you want to twist or not. When you apply the current, what happens? It hits very fast. So but it's in liquid. So you create a thermal gradient. In the same way like the mirage effect in the desert, right? The air becomes, it is different temperature for the air, and you have the mirage effect. That's the same thing here. Change the refractive index. So
almost continuously, right?
Because if you have a infrared camera, you see a lot of heat signature, but divisible. It's like a funny way to show that this you can do many things with carbon nanotubes. Thank you for your question.
Very nice. Any other question?
Harry Potter cloak of invisibility.
Any other question for the audience? Okay, if not, I would like to thank Professor Galvao once again, and we appreciate your nice talk. And perhaps people will contact you about your facilities, where some of us has some quite heavy calculations, and we can talk about that later.
Thanks again for inviting me. It is always a pleasure. I hope to visit you in person soon.
I hope as soon you can give a talk face to face.
Thank you. Have a nice week. Nice afternoon, everybody.
Same for you.
Bye.
Thank you very much.
Thank you.